Howdy, my name is Joshua Rhodes. I'm a postdoctoral research fellow at the University of Texas at Austin, the Weber Energy Group and the Energy Institute. And as they're getting my slides up here, I'm glad someone asked what LCOE was, because when I'm done with it, you'll understand what it is. I'm going to talk about it a lot. And since I work for a university, there'll be a quiz afterwards on it. So. All right, so I'm going to talk about a couple things. I'm going to talk about electricity, specifically the cost of electricity, the cost of generating electricity. I'm going to talk about solar, which is related to because it generates electricity, and how they relate, and in terms of pricing and all kinds of things, and an LCOE basis, and I'll actually roll through that. And then also, because this is a conference on efficiency, I'm going to talk about some efficiency work that I've been doing in Austin and how that relates back to what I'm doing specifically in how I'm presenting it. So, okay, yeah. So in this presentation, first, I'm talking about a project that I'm working on at the Energy Institute, which is a project we're calling the full cost of electricity, where we've tried to internalize as many externalities on the production of electricity as we possibly can, and we've tried to exclude as many subsidies as we possibly can. So basically, I'm trying to figure out, it's harder than maybe it's not harder than it sounds. It's a pretty hard project, but basically it's like, okay, if you're going to build something new, you have to pay some contractor to put in, steel and concrete and silicon or fiberglass in the ground to build something that generates electricity. Well, how much does that cost? And of course, as any good engineer will tell you, it depends. And in this case, it's going to depend on where you are, because resources vary from where we are. Demand varies. And this is a U.S.-centric look, so demand varies. Renewable resources vary. Lots of things vary. And then the second is I'm going to talk about some work I've done with Austin Energy, which is the levelized avoided cost of residential energy efficiency, analyzing some of the data coming back from their programs, and then I'll tie those two together at the end. So in this first part, assessing the full cost of electricity, you do this on an LCOE basis. Now, what LCOE is basically the levelized cost of electricity. So if you're going to build a power plant, and it's going to cost some money to put it in the ground, there's going to be operating costs to go along with it. There would be inputs, fuel costs. It's going to operate at a certain efficiency to turn fuel. You're going to burn something into electricity, or it's going to convert photons into electricity, or water into electricity, or all kinds of stuff. But the CapEx, there's a bunch of numbers. Where's that? Oh, yeah. So CapEx, the capital expenditures, operating expenditures, and fuels are some of the direct costs that we'll be talking about. The externalities that I'm going to be including are the criteria air pollutants, so SOx, NOx, PM 2.5 and 10. Specifically, the damages associated with the marginal damages associated with emitting those in a given location. And as you'll see as I get going along, I'm actually doing this on a county-by-county basis. So there's over 3,000 counties in the lower 48 where I calculated all of these things, and then I figure out in each county what the cheapest cost is. Now, some caveats. Again, subsidies are not considered, so the numbers I put up here for some technologies, particularly solar, may look high because I'm not taking into account the investment tax credit for wind. I'm not taking into account the production tax credit. Any of those things. I'm just curious, if you give everything as fair a shake as you can, what comes out the other side. Only generation, not transmission distribution. I'll talk about that a little bit later. And then, so we'll move on. This is a busy slide. Hopefully this is the busiest slide that I've got. But I just wanted to, particularly on some audiences that I've presented this kind of stuff to, particularly those that know way more about some topics than I do, they like to argue about numbers. So please, let's not argue about numbers too much today, or I'll be up here for 45 minutes if anyone has any strong opinions on these numbers. But the numbers that I've taken into this consideration for a couple different types of coal: bituminous, subbituminous, natural gas combined cycle, natural gas combustion turbine, nuclear, wind, solar PV utility, residential, and concentrating solar power. And in here, these are the base numbers for the capital costs, and $1 per kilowatt, to install these things. Now, anywhere you see something that has figure something or other, this is because I've ripped this out of a paper that I've got submitted for publication. I've actually calculated these costs on a county-by-county basis, because it costs more to build something in California than it does in Texas. It's just the way it is. The cost of labor is higher. The cost of materials are higher, particularly on the coast, and they are more so in the mid part of the country. And then next, I go into operations, operation maintenance costs that are fixed, variable capacity factor. Capacity factor is based on actual data from plants running in 22 NERC subregions across the United States. There's data that's self-reported by these power plants to the EPA, the eGrid. And so for the thermal generators, I've taken just the median value of those, and then for the renewable generators, I've just, particularly wind and solar, those are based on just on resource availability across, because, as you might know, the solar resource is typically better in the Southwest than it is in most other parts of the country. And then heat rate, the technologies that I'm considering are based what we call the best available commercial technology. And so this is like if you're going to go build something out there, not something crazy, is that I don't have carbon capture or sequestration in this, although I'm working on that. But the values here are based on what we consider kind of state of the art. If you're going to build something new, this is what you would shoot for. And then the price of fuel. This is in dollars per gigajoule because of the requirements of this paper, but actually dollar per gigajoule and dollar per MMBTU are pretty close. So if you're familiar with the price of gas, I have up here that I'm using a $5.35 per gigajoule natural gas price. That's actually $5.07 per MMBTU, which is relatively high for now. But again, I'm assuming a price of gas over the entire lifetime of a technology. And if you ever look at the price of gas, it just looks like a roller coaster. So we can say, oh, our gas price is really low right now. Well, that doesn't mean it will be, in 20 years. Interest rates for loans, years, length of power plant's going to be alive, and then also consider the non-combustion greenhouse gases. So their energy goes into concrete and steel and silicon and stuff, and so there's energy associated with those things before they get assembled in some fashion that then is some apparatus that makes electricity. And then if you're curious what LCOE is, here's a formula of it. So it's basically some math on all these numbers. And the main takeaways before I even show you my results are wind and natural gas tend to do well in most locations across the United States. Nuclear is the least cost option from what I've calculated in locations where the wind resources are poor and the cost of natural gas is high, because that varies across the United States as well. We say one price, but there's actually lots of different prices across the United States based on congestion, availability, and all kinds of stuff. Coal's actually competitive when you would not consider environmental costs, CO2, NOx, SOx, PM10 2.5, and then solar is the least cost option where CapEx is low, and I'll show you what that means here in a second. So this is some of my initial results. This is what I'm calling my reference case scenario. So based on all of those numbers that I showed and the calculations and a lot of underlying maps, particularly those that show various how much more expensive it is to build things in California than it is in Texas and so forth and so on. This is kind of where I end up. So basically, if you're going to build something new in a given location, natural gas combined cycle is kind of the lowest cost technology on a levelized cost analysis basis in most of the United States. And then wind is in green. So, natural gas is this orange, reddish, darkish color. And then wind is green in a relatively tornado-shaped location in the middle of the U.S. where basically the wind resource is good. So the wind resource is good, basically zero fuel cost, but it's available a whole lot. And then nuclear is this kind of dark bluish color up here. And so that's typically where the wind resource is poor and the natural gas price is high. So natural gas prices are actually pretty high here, and there's the edge of what we call the wind corridor in the U.S. So that's where nuclear shows up. Now, what what I thought would be kind of fun the other day is so the cost I assume for solar PV is relatively higher. It's like $2.7, $2.70 a watt, which is pretty high. But the problem with talking about solar costs is they've fallen 10% since I started talking, right? So, anyways, so what I'm going to do now is I'm going to start stepping down the price of solar and see where it kind of shows up on this levelized cost scenario. So if I step it down to $2 a watt, you might not have noticed. It's kind of hard to tell. This projector is a little bit dark, but this is where it first starts to show up in a little bit of the U.S. But it doesn't show up here where you most expect it. But it's actually showing up in South Missouri, where the price of other things are high, or the other resources are poor. That's where it actually, given these calculations, starts to show up at about $2 a watt. Again, remember, there's no incentives here, no ITC, no low interest rates. This is not. This is the cost of producing, the cost of producing a kilowatt hour. And then so as I set $1.90 a watt, a little more shows up over there, but then you start to get some in California and New Mexico, $1.80, a little more in Colorado, and then all the nuclear down there in Illinois and Missouri falls, $1.70. It's kind of like a flip book now, $1.60. Shows up in Minnesota up there, taking over where nuclear was. It was all Colorado's renewable at that point. And then $1.50, $1.40, $1.30, $1.20, $1.10, $1.90 a watt. Now, so there's a lot of solar on this map now as I've stepped down the cost of solar. What this map does not say that Arizona can run off 100% solar by itself. That's not what this map says. Please don't take that away from this map. This map just says, at that price, if you were going to build something new, that would be your cheap. If that's where you can get your capex down to, and all the other things the same, that would be your cheapest cost. It doesn't say that would be your greatest value of getting it, because the value is based on market conditions and all kinds of stuff and prices that you take. But if for generation costs for generating the next kilowatt hour, that's what this map is trying to show, is what technology that would be. Yes?
Could you say again which externalities were included in this cost scenario?
Sure. So I use the social cost of carbon, $62 a ton, CO2 for their median, their 3% discount rate. The NOx, nitrous oxides, excuse me, you can get that water bottle. Yeah. SOx, NOx, PM 2.5 and 10, so various sizes of particulate matters. And I believe those are lists. So I had those taken from a study by Mueller and Mendelson that looked at that on a county level basis. And so if you emit a marginal ton of some sort of an pollutant in a given county, that produces health impacts. Mortality, increased mortality, morbidity. Some of that plume carries on. It's all assumed to be put back into the county where it was roughly emitted. It's kind of how that whole system works. Yes. However, you can't really build anything you want to anywhere. So this is something I'm currently working right now which is a bit ugly, and I apologize for it. It's a lot of GIS work going into, but what this map is trying to show is basically what this map shows is where you're probably not going to build a coal plant based on the red, or these dark reddish ones here, which are EPA non-attainment zones. This green, which is not really availability of water, water availability, stream flows, reservoirs, municipal water availability is pretty low. And the colors kind of in this area and over in Appalachia, where you've got landslide issues and high slopes. And so basically this tan color, and I'll try to keep this thing a little bit steady. But basically these tan colors here are showing where you might be able to build something based on not having people having water and not ruining other things. So this will be worked into those maps before, but this is taking a while to compile, and so I'm not fully there yet. But I just wanted to give a counter argument to my own argument in terms about having lots of NGCC plants or whatever, or natural gas combined cycle plants maybe located in places where you couldn't. If I put this map on top of that, probably a lot more solar would show up, solar and wind, because you don't really need water. People don't really mind living around them as much, and you can put them on mesas, hillsides, so forth and so on, stuff like that. That you can't do other high types of capital investments. And all right, so some future work that I'll be working on, transmission and distribution. There's a big team of us working on this kind of stuff. I'm not the only one who do all of this work. So transmission and distribution cost, we'll be working there. We do a lot of grid simulations, particularly in ERCOT. So we simulate dispatch of power plants given demands of the other side of the equation, simulating the market versus just what it would cost to build something new. So if we incorporate these costs, what do dispatch curves like? At a certain amount of demand, there's certain types of plants that are said you will be online producing electricity because you're the cheapest one up to that point. But if we internalize all these externalities, how does that change what the bid stack could look like? Residential solar, threats and opportunities, traditional business utility models, which is a pretty hot topic right now, and amongst a lot of other things. So now I'm going to move into efficiency. Am I doing all right on time? 4 more minutes? Okay. So I'm going to go through kind of quickly some work on efficiency, particularly residential energy efficiency that I've done that will be incorporated into this study at the end, and I'll show you how I'm doing that. So basically, the data set underlying is I have a data set from Austin Energy that includes about 500 homes that have gone through energy efficiency programs, energy use before and after, but also have the cost of all those retrofits and the rebates that are associated with all of those retrofits. And again, and daily energy use before and after. And so what I wanted to try to figure out was, okay, I'm figuring out all this cost of generation. Can I figure out $1 per kilowatt hour for these efficiency things? And a lot of studies do this, but they do engineering models. Basically, they simulate what the retrofits will do, but humans don't always behave like computers, and so sometimes those numbers can be different. And so these aren't simulations. This is actual data. So I think it's pretty interesting. And as smart meters and things become more and more common, this type of analysis can become more and more common as well. But the main takeaway with this is so I considered. Cost of the utility from retrofits per kilowatt hour and cost of the homeowner based on the money they had to pony up for retrofits. And some retrofits are worth it to both of them, and a lot of rebates could actually be increased. And I'll show you what I mean by that. So here's some math that I did on all that data. I won't really go through it, and I'll just keep going. It was a mixed effects regression model if you're interested. But here's the results of said model, where I've taken into account things like cooling degree days, heating degree days, age of home, size. And then I get into what I mean by HVAC is if they got a new air conditioning system or not. By attic, if they got more attic insulation, window film, got new windows, and then replaced duct systems. Drape is they just covered their existing duct systems with loose fill insulation. Pretty cooling centric because that's where we are in this state. And then some interaction terms down here. Sometimes doing more than one retrofit's less or more than the sum of its parts. So hopefully this can kind of tease some of that out and give a little bit of better insight to what it costs. So down on these last three columns are kind of the result here, are kind of the results here. So what I've calculated for rebate costs, which maybe I should put utility costs because this is rebates that the utility gave, that it costs them about 0.7 cents per kilowatt hour from what was actually saved when they rebated someone getting a new air conditioning system, or 0.3 cents per R value added, 0.6 for replacing windows, and 0.9 for new duct systems. So it's all less than a penny per kilowatt hour of rebates associated that Austin Energy provided. And so this is less than the ERCOT average of 3.5 cents, or it's been over the past couple years, price for if you're going to get electricity on this wholesale market or whatever. And the next column, homeowner costs. So I not only had rebates, but I had the sum total of how much cash they had to give out to a contractor to actually do these things. And so for these homeowners, they're particularly going from kind of bad or pretty inefficient systems to more efficient systems, but it was costing them about 7.7 cents per kilowatt hour of the expected lifetime of the excuse me, of the retrofit. And so electricity, somewhere when you add all the charges together, you know, it's a tiered seasonal system in Austin, but it's somewhere around 11, 12 cents a kilowatt hour. So everything, so I should mention this, everything that's green means it's, for the rebate costs mean it's less than the average cost of electricity on the wholesale market, and for the homeowner, it means it's less than the cost of, you know, how much you're paying for electricity. So attic, about 2.1 cents. Windows were 17 cents, so I was like, I don't really know that replacing, you know, essentially going from single to double pane windows, in this case, by itself made, was economical by itself. But replacing duct systems was about 4.7 cents, so well below the about 11 cents that I'm kind of assuming. What I'm going to do at this point, so with this, what I'm planning on doing with this type of analysis is, for every location that I've calculated the cost of electricity, like in those maps, I'm actually simulating these retrofits as well. So what I hopefully will end up with are a map of the U.S. showing what is the biggest bang for your buck in terms of retrofit. Now that will be engineering calculations because I don't have data associated with, you know, all these locations. But my next step in this project will be, so I'll take this, I'll see the results. So I got to try to calibrate it against what the data are showing me in Austin, and then have a map of the U.S. that, you know. Because, I mean, it kind of makes intuitive sense, right? Like a more efficient air conditioner probably makes more sense in Phoenix than it does in Seattle, because you're going to use it more in Phoenix than you probably are in Seattle. But there's different technologies, different, and also different carbon returns on investment. There's, you know, different grids and different locations have different carbon intensities, right? So depending on when you're using these things on an hourly basis, some things might make more sense depending on when they're actually used. So there's this whole spatial and temporal aspect of, you know, electricity and efficiency that we're trying to get at here, because sometimes just the broad level, the high level view is good. You know, it's sometimes we do policy in this country with a hammer and it's like the same everywhere, which should be more of a scaffold depending on. I'm probably preaching to the choir at this point on that for you guys efficiency, but. Yeah, here are our contributors to this. Austin Energy CPS, who you hear for in just a second. Cherryland Utilities, and so forth and so on. And some that have given us technical input. I hope this slide is up to date. If anyone's in the audience and you're from this places and your name's in the wrong place or not here, I apologize. Yeah, so any questions? Are we waiting for questions at the end? Okay, so hold those questions. All right, thanks.